This is going to be a one semester course, about 16 or 17 weeks. I will show you what the plan is. But this is the basic information that you will need. So, all of you know me. Lectures will be in this room, Monday, Tuesday at 2:30. Tomorrow till about 4 o'clock. Might even end before that, I don't know, beyond 4 o'clock. We start today and we end near the end of May. So it's almost 4 months. For reference books, these are the two books that are available. One is Mohapatra and Par, which is a classic book, and the Jungian thing, which is a recent book. I will try to see that both of these are available in the library. So you can decide whether to buy them or not, if you want to how to do it. However, what is available right now is lecture notes of SCRC school lectures that I gave about 4 years ago. Another thing that is available is, of course, the lecture notes that you will get from the every class. And in case you are interested in some of the topics that will be covered in the future, you can go to my webpage, find out the course that I did last year, okay, and you will get some idea of what we do. Although this course will be slightly different from what was there last year, it will go on very similar. I expect that you should know at least introductory part of particle physics. So I suspect every one of you has done at least one course of particle physics. So I will assume some knowledge. If there are some things that we need more than what you have done, you can ask me immediately. I can tell you to put it in a blank box, and we will solve the blank box later. But anyway, at whatever point of time, if you want to ask a question, stop me immediately. Don't wait till the end of the class. This course is going to involve a lot of experimental part, in the sense, a lot of emphasis on experiments, detectors, data, and so on. Because it won't be a purely theory course. But I think that most often theory knowledge you can get by reading books like these two. But knowledge about experiments is something that is not available readily in books. So therefore, I think it's important to tell you about those, and that's what I do. There is a link here, course convention plan. If you go to my webpage and click on the webpage, then you will find that I will upload each day's lectures there, and perhaps also plan for the future. The webpage is obviously not this. The webpage has a different name. The webpage is theory. Definitely go to Amol and you will find a link to this course. I think it is good for your history. Okay. Fine. Okay. So this is fine. So let's go to actual lectures. So the way I'm going to do is I'm going to have complete some preliminary preparation in terms of this PDF file with some figures, and then on top of that let's go right into the talk. So let's see how this goes. So this is the plan of the course. So I divided the course into 5 modules. So there is about 3 or 4 weeks from a module. So the first module is going to be some preliminary part, which one can call as neutrinos inside that. So today, for example, I will give you some basic introduction to neutrinos, and an overview of what other things that are happening. Tomorrow, we'll look at neutrinos before oscillations, which means that so even before the neutrino oscillations were discovered, we knew about neutrino masses, their velocities, their cross sections, and so on. So various properties of neutrinos are anyway known before that. And before we enter full-fledged into oscillations, which is the main purpose of this course, we will talk about the things that we knew even before we discovered oscillations. And then next week there won't be a class because I'm not going to be here. The week after that, we will look at the atmospheric neutrino puzzle and the solutions to relative oscillations. So we spent this week talking about this puzzle. Again, in the week 4, there will not be a class. The reason is that there is a conference in TIFR which is on neutrinos. So although the conference will be slightly advanced, it's about supernova neutrinos and their oscillations. You are all welcome to come for the talks. Although I won't guarantee that talks will be understandable after listening to just 2 or 3 lectures. Okay, but you can decide about it. So this is the first module, which is about oscillations of neutrinos inside vacuum. The second module is going to be about oscillations inside matter. So this all starts with the puzzle of solar neutrinos because that is the physical situation where we have to deal with things inside matter. And to understand this solution, we will have to spend about 3 or 4 classes. We will talk about oscillations in the matter density which is constant, and more importantly, oscillations in the matter density which is varying. Inside the sun, the matter density is varying. And then we will come to the solution of solar neutrinos. So module number 2 basically is solar neutrinos. Module number 3 is going to be combining these two. It's because see, atmospheric neutrinos will tell you about oscillation between 2 neutrinos. When you do solar neutrinos, they also tell us about oscillation between 2 neutrinos. However, we know that there are 3 neutrinos. Okay. Therefore, by some means, we should be able to combine the atmospheric part with the solar part. And then they come with a coherent picture of neutrinos in the 3 flavor. So third module is going to be about the 3 flavor. So we first figure out how to combine atmospheric and solar neutrinos in a 3 neutrino framework. And now that we have combined them, then we can ask many more questions and solve many more problems. So in fact, now we can look at oscillations with 3 neutrinos, and then they have many more interesting features than just atmospheric and solar. In fact, the future of neutrino physics is in long baseline experiments, which means that you have a source somewhere which produces neutrinos. You pass some of the neutrinos through Earth for a long distance, like 1,000 kilometers, 3,000 kilometers, 5,000, 10,000. Okay. So it's very long baseline. Baseline means the distance between the source and ejector. So we look at these, and then we look at on the point of sterile neutrinos. It means we try to look at signals of physics beyond the standard model that we see from neutrino experiments. So this section is what I call as section of 3 neutrinos. So by this time, around the end of week 10, which is the beginning of April, we will have finished most of the part about neutrino oscillations. So at this time, I expect people to be comfortable with doing calculations with neutrino oscillations and have some understanding of basic detectors and so on. So I'll have a midterm around this time, first week of April. You will notice that each module has a homework. So there will be 5 homeworks. And expect that people are on time with homeworks. Because then the module structure will work well if people are fine with homework. Yeah. Otherwise, keep on using it. After the midterm, this is a module which I can call roughly as the theory module. So we will worry now more about where the neutrino masses come from. So this is, we'll start with the standard model Lagrangian, which I suspect you already know. And we'll concentrate on how to give mass to various particles in the standard model. So I expect that at least some of you are doing QFT1. Who are doing QFT1? So at least some of you are doing it. Okay. So although it's not, I'll cover everything that's strictly required. However, it will be by the midterm of QFT1, you will be able to appreciate this part slightly better. So we talk about how the mass is generated in the standard model. Then we talk about what's called as Marana neutrinos, which means that the neutrino can also be small algebra. And we will worry about how interesting things can happen if neutrinos are in fact Marana particles. And then we come to various mechanisms by which neutrinos can get a mass. So, as you know, the standard model as it was for 20 years or so did not have neutrino masses. Neutrinos were massless. Now that we know they have mass, we try to give them some mass. And we will learn here that the ways to give masses to neutrinos are much more than the ways to give masses to quarks and other. So there is basically just one mechanism, which is called a Higgs mechanism, which can give masses to quarks and leptons, charged leptons, I would say. But once neutrinos come into the picture, you have got many more ways of giving them masses. In fact, there are quite a few mass mechanisms, and we look at these mass mechanisms. And centered around these, there are going to be many theoretical ideas, and I will spend this module talking about theoretical. And the last module, we'll spend a lot of time, in fact, at least 2 full weeks, talking about various experiments, detectors, analysis of data, statistics. So when can we say some result is true, when can we say it's not, how can we quantify results, and so on. So, one reason being that is, of course, very important for our INO students, because they'll be worrying about it throughout their life as a PhD student at least, and hopefully also beyond. But also for other students, I think in a course like neutrino physics, it's important to appreciate how the detectors work, because then only you can try to make some practical progress. And then I will have one last week where I will talk about applications of neutrinos in astrophysics and cosmology. So people have heard about neutrinos supernova, neutrinos that may form part of dark matter, neutrinos that leave their imprint in this cosmic microwave and radiation, neutrinos that help in the nucleosynthesis of light elements, big bang nucleosynthesis, and so on. So we will talk about them and the result. So I expect that by this way, about end of May, we'll be able to finish our course and apart from these homeworks and midterms and final, I will give you some projects to do. The project will actually form part of these 2 weeks. So some projects are going to be professional experiments, some data analysis. There will be some projects purely theoretical, when we calculate something, but then they will be incorporated as part of this. So these talks, in fact, these lectures will actually involve initially one of you coming and presenting the project, and then I will take up from that and give the rest of the lectures. So these are our plans, and let's see how things go. So 5 modules that are in front of you. So if you have any questions right now, you can ask now, or I will go to the give you a few seconds to have a look at this. As you see, the schedule is rather packed. You can see that I am not actually giving any topic a lot of times. These are the things that I think one should know by the end of the physics course. So therefore, most of the lectures should happen according to that. I have left some brown things or tutorials where I can fill in with the times, but otherwise. You can come and ask me questions about the course individually. Usually the time to meet me is after 7 o'clock in the office. So maybe during the day it's hard, but between 7 and 8 I am usually in my office. So that's the time to find me if you have any questions. Or of course in the class. So what I will do today is I will just give you an overview of neutrinos, okay, in a very simplified version. So kind of more like a popular talk, more things that you will. Okay. And from tomorrow onwards, we will again come back and start doing things in excruciating. Okay. So in case you have not realized this earlier, this is to emphasize. Neutrino sources in nature are actually quite a lot. Perhaps we can start from this end because this is the natural sources. So sun happens to be the largest source of neutrinos that we have. So beside sun, we have different reactions, most of which give out UV or electron. The number of neutrinos coming from the sun to us is very large. The rate is about 6 times 10 to the power 11. Per centimeter square. So if you want to put that in perspective, it means that so through your palm, number of neutrinos that pass through so this means that number of neutrinos that pass through your palm when your palm faces the sun is the power 12 per second. So it's a large flux. And among all these entries that I have here, this is perhaps the largest flux of neutrinos. Next will be something like a star, like a supernova, which explodes and gives out lots of neutrinos. So we will deal with that in detail in a single. However, number of neutrinos that come out from supernova is of the order of 10 to the power 60. So we are talking about very, very large. And these 10 to the power 60 neutrinos come out within about 10 seconds. So that's very large flux, although it happens for a very short time, only for about 10 seconds. Then let's come to the Earth. So Earth has radioactive elements, uranium, thorium, potassium, and so on. Almost all nuclear reactions will give out neutrinos, and therefore the natural radioactivity inside the Earth actually gives rise to a lot of neutrinos. We have just recently started being able to identify these neutrinos. So these are what's called as geoneutrinos, and it is only maybe within the last 4 or 5 years that we can actually identify neutrinos coming from the Earth's crust, identify them as geoneutrinos. So we'll also talk about that. These are detected by scintillation detectors. Okay. The idea is these are neutrinos which have energies of the order of MeVs or hundreds of keV. Okay. And the reason that they are not identifiable directly is because neutrinos from the sun, which are very large in numbers, also have the same energy. Okay. So the reason we are able to identify geoneutrinos now is because we understand solar neutrinos now. So we know exactly what a solar flux is. We know what happens to this flux is by oscillations. So we know exactly how much UVs appear on the Earth from the sun. Then we look at the neutrinos that come from the Earth and we subtract out this background, so on and so forth. And then we identify what's happening. So in order to be able to identify geoneutrinos, we have to be able to first understand solar neutrinos and subtract them. That's what we do. This is done counter for those of you who know. Another source of neutrinos is the atmosphere of the Earth. So here what happens is, so the whole universe is filled with protons. Protons of various energies, starting from GeV all the way till 10 to the power 20. These protons move through the galaxies. They get accelerated, they rotate because of magnetic field and so on. So everything influences them. And they arrive at the Earth and we call them as cosmic rays. So when we say cosmic rays, we basically means many protons. So these protons enter the atmosphere of the Earth. They interact with nucleons, nitrogen, oxygen, carbon, whatever. When they interact with nucleons, they form ions along with other things. And these ions will decay and form neutrinos. So this is the basic process by which we will see neutrinos inside the atmosphere. So whenever one says atmospheric neutrinos, So basically means neutrinos that come from cosmic rays and are produced in the atmosphere. That's the only mechanism for atmosphere. So these are of course all natural ones. This is also a natural one. So for example, there are things called as gamma ray bursts. Astrophysicists have some guesses as to how they originate. Sometimes they originate because there is a star circling around the black hole or neutron star, which attracts all the material from that, and finally in a huge burst, the whole star gets enveloped by this black hole. In that case, you get a gamma ray burst. That's one mechanism. However, there are many other mechanisms for gamma ray burst, and we have not been able to say exactly how the gamma ray burst functions. Depending on the mechanism, there will be different signatures of neutrinos. So what we have now is we have detectors which in principle would be able to detect neutrinos from such gamma ray bursts. However, right now we have not observed any gamma ray bursts in that detector, but I will talk about the detector sometime. So we are hoping that soon we will be able to see these astrophysical accelerators. So neutrinos which can have large energies like TeV or TeV. Then of course there is relic neutrinos, which are the cosmic microwave background neutrinos. So you know that people have heard about CMB, like cosmic microwave background photons. So this means that wherever in the universe you go, you have about 400 photons in every centimeter. And this is true here, this is true even at remote place inside, in between galaxies, where there is nothing else. So that makes photons the most abundant particles in the universe because it's 400 per centimeter cube, almost everything. And they have a temperature of about 3 Kelvin. So this we know, in black body spectrum. Just like photons, neutrinos are also light particles. They also decay quite early on, and they are also very, very, very nucleus. So these are what we call as the relic neutrinos, or we call them as cosmic background neutrinos. I think it is called as cosmic Big Bang neutrinos. And if our understanding of cosmology is correct, Big Bang, expansion, decoupling, blah blah blah, then we will have about 330 neutrinos per centimeter cube all over the space. Again, these neutrinos are not yet detected. This is only theoretically that we know they should be 330. Okay, but this knowledge is rather solid because the current cosmology matches with the observations. Yes. So these neutrinos have a temperature just below the photons, so about 2.5 degrees Kelvin, which actually corresponds to 10 to the power minus 4 electron volts. So extremely low energy neutrinos. That's the reason you can't detect it. Okay, so in fact, at some point we talk about attempts of detecting these neutrinos, and right now instruments like torsion balance, for example, have to be improved by a factor of million or so in sensitivity if you want to detect these neutrinos. Okay, so we are very, very far from detecting these kinds of neutrinos. However, cosmology tells us that these must exist. So these are all natural sources. Of course, we have nuclear reactors, and all nuclear reactors we use.
We call it cosmic microwave radiation. It has some other origination, cosmological revolution. So it's like that. Here, cosmic, as you said, cosmic microwave, they can found 400 per centimeter cube of neutrinos or photons everywhere. So this is that reason that we can find some number of neutrinos everywhere. That is why it's called cosmic Big Bang neutrinos, or it has some origination related to that CMB origination.
They have the same origin. See what happened after the Big Bang, all particles were produced, okay, by whatever reactions. Okay. Now what happened is many of the particles reacted with other particles, okay, and as long as they reacted with other particles, they were kept in equilibrium. Now the universe kept on expanding. When the universe expanded, at some point of time, the expansion was so much that the reactants could not come together. So at this point, what I call as decoupling happens, which means that the particle now does not interact with other particles. So why did the cosmic microwave radiation, the photons? At some point of time, the photon density became so low compared to the expansion of the universe that the photons after that point didn't even interact with anything else. So the photons were there, and after that they just expanded because space expanded. That's it. Similarly with neutrinos, exactly the same thing happened. Okay, they were produced at a time of Big Bang. Initially they kept on interacting with other particles. They interact with electrons, make some charge current, interact with nuclei, make something else, blah blah. At some point of time, the universe expanded so much that then the neutrinos didn't interact at all after that. So whatever neutrinos were at that point of time, the distribution got frozen and they just expanded with space. So origin is the same. So the reason they are called cosmic Big Bang neutrinos is because they basically produced during Big Bang. So origin of the photons and neutrinos is exactly identical. In fact, one of the nice projects to do sometime later on is to try to calculate this number 330. So you will see that the way to calculate this number is exactly the same as the way to calculate cosmic microwave background radiation. Okay. So I'll give this to one of you at some point. So you do both the derivations and look at them side by side. In fact, the factor between them is also some nice, some 4 by 11 to the power something. Okay. So, the things are very, very simple. Yeah. So artificial, of course, are created at nuclear reactors and at accelerators like CERN. However, neutrinos that are created at something like CERN actually are never detected. Okay. Because neutrinos interact very, very weakly. Okay. So when they are produced, they just travel out through the detector. So in a detector at CERN, if you want to see how the neutrino looks, it basically will not be seen at all. So it is counted in what is called as missing energy. Therefore, neutrinos actually form a lot of background for looking at new physics like supersymmetry. Many of the new physics phenomena involve missing energy because there are many particles in like supersymmetry which do not interact inside detector and go out. Okay. But then if we see something in the detector, like a particle has gone out and lost some energy, we cannot immediately conclude that it has to be a new particle because we know of neutrinos which can escape and therefore will give you some imbalance energy. So therefore, at CERN, neutrinos which are produced will not be observed. Okay. However, you know the properties, so we can reconstruct the energy in okay, so, but that is a part of it. So I just wanted to show you the sources of this problem. This is something I already mentioned. I wanted to emphasize this once more. Comparing number of photons and number of neutrinos in the cosmic microwave background radiation. So it's about 330%. Now note something, that since we know that these exist all over the universe, if we knew mass of neutrinos exactly, we will know what is the density of mass density of neutrinos. So in fact, if we know mass of neutrinos, this will tell us what fraction of dark matter is neutrinos. It's a very simple calculation. We will do it at some point. Another simple thing, just to emphasize, is that of course they are the lightest particles that we know of. Apart from photon, which is massless. Next lightest that we know of is electron, which is 511 keV. As far as neutrinos are concerned, the mass is at the most 1 electron volt. Okay, so 500 keV to 1 electron volt, so a factor of almost a million. So they are almost a million times better than the electrons. In fact, they can even be lighter because all we have is the upper limit of their masses. So therefore, there has not been any direct mass measurement of neutrinos. So there has been no experiment which will measure a neutrino mass and give you the neutrino mass. All these experiments have done is to give you some upper bounds. The way we know neutrino masses right now, that they are non-zero, is because we have these atmospheric neutrino and solar neutrino anomalies, which we know are oscillations, and therefore they have masses, because oscillations will give masses. That is the only way that we have to say that neutrinos have masses. Okay? There are no experiments which can actually measure the mass today. We'll talk about in detail, in fact, just to know. And this is again something I want to firstly, they are the most weakly interacting particles we know of, mainly because all other particles have charges. Okay. So leptons, quarks, all have charges, charge them. Therefore, they interact with light. And the interaction with light is sufficiently high that you can see. So, by definition, they are invisible because they don't interact with light. And to give you a comparison of how weakly interacting they are, this is a number to keep in mind. So, if you have a radioactive source in the lab, few KEVs, usually we use shielding to shield this source, shield us from the source. Okay. And we use net shielding, which is, I don't know, maybe this thing, 20 centimeters, 30 centimeters, 50 centimeters, maybe 1 meter.
Sir, aren't they scattered by photons?
Neutrinos? Yeah. No. They don't interact with photons. So they can't be scattered by photons. Yeah, so taken the source in the lab, we can easily have a late shielding of 50 centimeters and can be reasonably sure that none of the alpha, beta or gamma radiation will escape this. So normally 50 centimeters is enough. Now, let's say we want to do the same thing with the sun. Let's say we know that sun gives what 10 to 12 neutrinos per centimeter square per second. We want to put a late shielding between the sun and us, okay, so that these neutrinos will not reach us. So that's not so easy, because if you want to look at the thickness of the late shielding, that's going to be several light years. Okay, so basically means between the sun and us is almost impossible. But also it essentially means that neutrinos can come to you from almost everywhere in the universe without doing anything. So one good application of this is to be able to see inside stars, for example. Let's say something is happening inside the core of a star, neutrinos are emitted, they will come to us directly without scattering anywhere. Even the sun. Okay, if you want to look inside the sun, let's say you have nuclear reaction inside the sun. Nuclear reaction will produce neutrinos, will produce light. Okay. The light produced in the core will not be able to come out. In fact, it is scattered, no? Because sun has a lot of matter. What is the density of the sun?
50 grams per second.
So about 150 grams per cc in the center, and therefore decreases as you come out. So 150 grams per cc, of course, light cannot come out. Okay, it's very simple to stop light. I can even this group can stop light. And this laser light, this chair can stop this. So 150 is too large. So light will always keep on scattering inside the sun. Okay, in fact, an estimate, such a big number, is if you want to track a photon scattering inside the sun, which will come to the surface and come to the Earth, the photons will take about 1 million years to come to the surface. Now, what we look when you look at the sun is the surface of the sun. So, the photon that you see on the surface of the sun actually started from the center about 1 million years ago. Okay. So, when you see the sun in light, you see a very old sun, you see a 1 million year old sun. When you see the sun in neutrinos, you see 8 minute old sun, because light takes 8 minutes to come from the sun. Okay. So, just one more piece of information.
But neutrinos are undetected, so how to see the core of the sun? Because you are not seeing the neutrinos somewhere.
No, so I am not saying the undetected. Most of them are not detected, but we detect some of them. Okay, so I will give you some numbers. After the trillions of neutrinos that we receive every second, we have a detector now. We detect about 10 neutrinos per day. Okay. So most of them will pass through, but we will see 10. And statistically, then we know what happens to neutrinos. There is some curiosity that one should have. Okay, since all of you have done the particle physics course, you of course know these things. I just want to say it once more. Neutrinos will be part of leptons, corresponding to E, U, and tau. We have mu E, mu and mu tau, lepton neutrino, muon neutrino, and tau neutrino. Each of them will have its antiparticle. So we have three neutrinos, don't have charge. They are fermions, spin half particles, almost massless. There is a one electron volt, and they undergo Dighe interactions. So what I tell you today is I tell you a brief history of neutrinos, starting from their discovery and its problems of puzzles with solar neutrinos, puzzles with atmospheric neutrinos, how they were solved, and so on. And tell you what our current knowledge is and what the future is. So this is going to be more of an overview of what we are going to cover in this course. Okay. So discovery of neutrinos started from study of nuclear radioactivity. So people had known the radioactivity in 1900. Because saw the X-rays in 1900. After that, people also studied alpha, beta, and gamma radiation. When they looked at the beta radiation, okay, it was expected that beta radiation means that you have a nucleus which decays into another nucleus and an electron. So a simple reaction like this: X goes to Y plus electron. And now, of course, if you have only two-body decay, it means that the energy of electron is fixed. So if you want to look at the energy of this electron, for example, this will just be the mass of X minus mass of Y with appropriate units. This perhaps is the last transparency when I have C squared, okay? I have C equal to 1 of the So what we expect is, if I make a plot like this, where x-axis is electron energy and y-axis is number of electrons, all the electrons that are observed should have the same energy. And that energy should be equal to this, approximately. So what I expect is I observe a peak like this here and nothing here. Ideally, I should have seen nothing here except for a peak exactly like this energy. What was observed was very different. What was observed that you don't get this peak at all, but you get a curve that looks like this. It starts from almost 0, it is a peak and comes down. So it's continuous. So neutrinos can have, not neutrinos, sorry, electron can have any energy between 0 and this maximum energy. This was the problem. Because all that we use to get to this relation is conservation of energy, conservation of momentum. Okay? And as we know, we don't want to violate this. 30s was the time when quantum mechanics also was not very well established. So in fact, there were postulates made which said that atomic phenomena or quantum phenomena do not respect conservation of energy and momentum. Some very authoritative people said that maybe at atomic level you will not have conservation of energy and momentum. However, Pauli had the audacity to come up with this postulate. It is possible that we have one particle which we don't detect, just escapes. So in 1932 we postulated this part. So now what happens? Now it means that the energy difference between the X and Y nucleus, their masses, is split into neutrinos and electrons. So therefore, even if you ideally look at neutrino spectrum, you can also do something. So this in principle solved the problem of energy and momentum conservation. However, this one is the postulate. At that point of time, when Pauli postulated this, he just said it as a way to resolve this. He himself did not believe this. Because in fact, the first time that he sent this paper for conference proceedings, he actually didn't go for the conference. He made an excuse of going to some village hall to dance and saying that I cannot go to this conference. I am just sending this as a note. So his note was basically read out in the conference. That's what it is. Fermi later on did a lot of work on this. He showed that if indeed there is a neutrino going out, then he had this Fermi theory by which he could calculate the decay rate of beta decay, and he could predict the spectrum of these electrons. And once that was done, things were on a formal footing. However, that was the time when you could not just postulate the particle. People usually would snigger at you to postulate the particle. Nowadays that doesn't happen. This was the cartoon, and from some time back. So actually people commented on this. Yeah. So it says that the particle is too weakly interact with the detect. You can't just take it on faith that you have discovered it. Yeah. This will be physicists from 1930s and these people are physicists from 1990s. Okay, so remember that the postulation of neutrino existence happened in 1930. Okay, so that was the time when we postulated this. From that point onwards, people started using detector to detect neutrinos. Because unless you detect it, it will be taken as solid evidence. So it took people about 25 years to actually see the neutrino. Because we did not have a theory of weak interactions there. As a result, it was not known how weakly interacting they are. Okay? So you first assume that okay, the interaction rate is maybe 100 times weaker than electrons. You build a detector, you try to look at events, you see nothing. You say okay, fine, not 100, 1,000, 10,000, and you keep on going down and down. So which means that every time you do not see neutrinos, you build a bigger detector and you wait for longer times. So what people did is they knew there are nuclear reactors which will produce neutrinos. Then you have to have a detector kept close to this reactor, okay, and hope that at some point of time a neutrino will come in, will interact with the detector, and we will be able to see this. Because what will you see in the detector? Neutrino cannot be seen while coming inside. Okay, it will hit again electron, and electron will come out. So you will see that in the detector there was nothing. Suddenly, in the middle of the detector, some electron came. The electron got some high energy, almost no reason. So people built such experiments, kept on improving them, and finally the one that succeeded was the experiment that was this experiment by Rinosenko. It's called as a $1 million experiment, particle experiment, because the experiment cost about $5 million, and it saw 5 neutrinos. Each neutrinos essentially cost almost $1 million. Okay. So what is the reaction that you wanted to have? So let's look at this from the point of view of the experimentalists who actually were doing the experiment. So they knew that they had a nuclear reactor. The reactor produced antineutrinos, nu E bar. So this was expected. Now, they knew that this reaction should happen in principle. Because just like you have a beta decay of neutron, so neutron will give proton, electron, and something which is missing. We expect that this missing particle will hit the proton, give neutron and positron. That's what we expect. And then the claim is we have to identify this positron. Okay, so that is the aim. So the question is how to identify this positron. A good thing that positron does when it travels to matter is that it loses energy because it's charged particle. So charged particle moving through any matter loses energy. Okay. When the energy of positron is almost zero, so it's almost stopped, it can get captured by an electron. It can annihilate the electron. So E plus E minus annihilation will produce 2 photons with energy of 511 keV. So this is okay, right? So E plus has a mass of 511 keV, E minus has the same mass. They are at rest almost, combined together, and the outcoming energy is given out as 2 photons. Okay. You know that it can't be given as 1 photon. If you don't, then you should try this one. Okay. You can try energy momentum conservation. It will show you that you cannot have annihilation of 2 particles giving you only 1 photon. Okay, you valid energy moment. So you have to get 2 photons. These 2 photons again symmetrically everything is at rest. To conserve momentum, 1 photon will go here with 511 keV, 1 will go here with 511. So everything will go.
Can you measure the E/M ratio of the outcoming this positron? E/M ratio.
How much will you take the positons?
In the same way, in the detector, I am seeing that some particle came and my detector is giving some particular pulse at some point of time, and we can try to see if the particle is positively charged or negatively charged. That can be seen.
In principle, yes, but then you have to wait till the particle positron reaches the detector. The thing is, before it reaches the detector, it's going to slow down and elect an electron and give out these two photons. So you cannot have detecting elements at every point inside the detector. See, remember, this is a neutrino detector. Okay? So you can't make a small detector, you have to make a very large detector. Okay? If you want to detect the positron immediately after this production, it means you have to be everywhere inside this detector at once. So normally what was done here is you had a big detector, outside the detector you give photon. Okay, so I forgot, the detector was actually made up of So yeah, this was basically water with some scintillator and cadmium chloride. I will come to why we need cadmium. But this was the principle. Produce positron. Once you produce it, you can't escape. It has to undergo this reaction, and it gives you these two, which actually is good. Okay? Because see, detectors intrinsically have lots of electrons. Okay? So although you say that what you want to see is arbitrarily one electron shoots up, it could just happen because of some pattern. Okay? So it's good to be able to see a combination of signals such that only if you have a signal will this be a unique feature. Okay? And random occurrences won't be able to do this. So it was good that you actually could obtain this signal where you get 2 photons of known energy, 0.5 meter. So this was one. Even with this, there could be problem because maybe you produce positron by something else and not by this process. Okay, whereas now you are going to identify a new particle. So it's very important that you are really sure that this actually was the reaction that you wanted. Okay. So this is not enough. You identify this positron, but you also have to identify this neutron. And to do that, technique used was this. So people knew that if you had cadmium 108, okay, if a neutron hits the nucleus, it goes to cadmium 109. However, this is not a ground state, it's an excited state. So after some time, it decays to the ground state and gives a photon. This lifetime also is known. So although I don't have it here, I am not sure what the lifetime is. So therefore, okay, good, 5.5 microseconds. Okay, so what will you see now? Okay, so in detector, you see that out of nowhere, you see 2 photons of 0.5 eV. After that, 5.5 microseconds after that, you see another photon, okay, which also have energy in certain things. Now all these 3 things are unlikely to happen simultaneously. Therefore, this becomes a good signal. And what the Reynolds and Cohen did is exactly this. So this was a nuclear reactor. The flux was about 13% meters square per second. It's almost like the solar flux, 10 times. 100 times. These are all photomultipliers. Photomultiplier means that the photon comes, they will detect the photon. So neutrino will come, interact with proton, give a neutron and an electron and positron. Positron will give 2 photons. Okay? So one photon will be detected by this photomultiplier, another by this photomultiplier. Okay? So you get these 2 photons. This neutron will be absorbed by cadmium. This will decay to ground state, give 1 photon. So once this is done, then we are sure that this actually was a neutron. So this experiment ran, I think, out of 1 year or so. In the 1 year, they found 5 neutrinos. That's the description. So this was the first time that one actually saw a neutrino in terms of interaction. So reservedly, these people got Nobel Prize in 1995, and 40 years after that, they did it. In 1956, it was accepted that they had discovered neutrinos. So it was Pauli postulated the neutrinos in 1930. It was in 56 that we said neutrinos were neutrinos. This was again a neutrino. Okay. At that time, there was no distinction between neutrino and antineutrino. People didn't know what is what. People didn't know about Nui, Newton. Okay. So just the neutrino. So if you stop over the clock at 10:56, all we know is that this experiment told us that there is indeed a particle called as neutrino, which will participate in this interaction. And this was emitted from a nuclear reactor, so we knew that it came from nuclear. So let me hold for a few seconds and see if there are any questions. So now people knew there are neutrinos. Okay. So of course, once this neutrino was found, people thought of detecting neutrinos from other interactions. So another interaction where you knew that neutrinos would actually be there was ion decay. So people of course knew of ions. And
So at that time they were knowing about neutrinos and antineutrinos.
no.
So they have taken antineutrinos specifically to produce positrons.
Yeah, so the reason was again the following. They didn't know antineutrino. Although they knew that in beta decay, neutrons go to protons.
Yeah.
Okay. So they knew that something will come out of this. They didn't care whether it was mu or mu bar. The reason that this reaction was considered was because this involves protons. Okay. It's very easy to have protons, essentially because water is cheap. So detector again, you see mainly it was made up of water. You need big detectors, so you can't use expensive elements. Okay. If you have got water, each molecule of water gives you 2 hydrogen atoms, so you have 2 protons every time. That was the reason that this reaction was used. But even now, this is the major reaction that people try to use, simply because water is cheap.
This is the opposite reaction of beta.
Yes.
If you only knew beta decay, this is the only thing.
But you know, people also knew nuclear decay, which gave out positrons. Okay, because although neutrons can go to proton in vacuum, okay, if you have proton as a part of a nucleus, it can decay to a neutron. That's basically nuclear decay.
Beta plastic. People knew about beta plastic.
Yeah, people knew about beta plastic.
So why did you take this 0.5 unit to assume that C class?
So first thing it will do, see, even electron, it loses energy very quickly inside matter. So similarly positron also, is the same tends to lose energy very, very quickly. Okay, especially when energy is about absorbed of MeV, you lose energy within a few centimeters or so. So within this distance.
So why do you assume that the E plus C minus combination happens after the
That's because we know that positron will lose energy very, very fast. So of course when you say 0.5 MeV, you have into 0.5 MeV plus minus whatever.
No, I was just thinking that it will be quite large because the Q value of this reaction is of the order of MeV because this is reactant. So 0.5 plus minus big.
But not very much. You can figure out exactly how much it is. I don't think this particular will. Okay, so that was discovered. Now, people knew that ions decay. So people also knew that ions decay to muon and nothing else comes out. So in fact, this is one more dramatic way of looking at energy momentum loss observation. Because what will you see here? You have an ion decays to a muon, nothing else comes out on the other side. Okay. So very clearly something is happening. Ion and something else is going inside. So people knew that the decay of ion is a reaction where you get some loss of energy. Therefore, you expected that this must be a neutrino. This was expected. So some neutrino will come out. Of course, we didn't know of any other kinds of neutrino. So every time you do an experiment, it would work similarly to this ionoscope. However, this time they decided not to use what was the target, but use iron. They used iron simply because the Second World War was over at that point of time, and there was the USS battleship available for the experiment. This was in a nuclear war. And they decided to make the battleship as a detector. So it's almost like iron, right? It lots of iron. The good thing about iron is that it has large density, so you get more target atoms. Right? So they use iron. They wanted to look at this reaction. That they had some neutrino. If it hit some iron, it will do something to the nucleus and will give you something. Okay? What they expected was something similar to the earlier case would happen. So they expected that electron will come or a positron will come. So I have detected which could detect positrons. Now, once they did this experiment, I think this also ran for around the order of a year also. Number of neutrinos, number of muons they observed was 29. Number of positrons they observed was 0. So one important thing was that they observed 0 number of positrons. So although the experiment was made to detect positrons, they didn't observe any positrons. So this was one major reason. There are no positrons. On the other hand, they found that you could actually get muons instead of positrons. In fact, number of muons that you got was almost the same in number as the number of positrons you expected. So they expected about 30 positrons, but they got 30 positive muons. So this was puzzling at that point because it looks very fine that this interaction gives us a particle which is not detectable very easily. We know such a particle, it is the neutrino. So this neutrino we know would give positron. But you see no positron, but you see positive. And the solution to this was that the neutrino that came out of this reaction was different than the one that came out of the beta neutrino. So this neutrino therefore was then named as muon neutrino. And this is the time that people figured out that therefore just like corresponding to electron we had muon, corresponding to electron neutrino we had muon. So therefore this was the discovery of the second neutrino, which now we call as muon neutrino. So the experiment principle is the same, of course. Ion decay produces neutrinos. In a shot on this proton target, it basically means ion target that they use, and they give one question. So these people actually got Nobel Prize much before the earlier ones. Okay, but that has different social. So this was the discovery of the second neutrino, and then we knew that you had two neutrinos. And then we sort of knew that therefore we expect that each generation will have.
So at the time they were knowing that there is a second family of black holes.
Yeah, so at that point, see it was 1962, which means they knew the strange quark, they knew the charm quark, and they knew muon. Okay. So all these three we already know. Okay, so therefore third family was known except for this last piece. It was earlier people thought that families could be only made of two quarks and one lepton. Neutrino could just be independent. Once you figured out this, it actually gave impetus to saying that family. Because like everything else, you could now see families of 4 particles each, 2 quarks.
But they have got Nobel Prize earlier than discovery of neutrino.
Yeah, I think that is independent discussion. I don't know. US. I think they were in Brooklyn.
Sociology is.
I don't know. I don't know. Sorry. I suspect the way to get pion actually is to accelerate protons and hit them on the target. Yeah, this will be nuclear reactors. Yeah, of course, this also is. Yeah. So this is okay. It will come up again and again. The way to get pions, standard particle physics way, is to get protons, accelerate them at very high speeds, shoot them on a target, at any target. We produce very rare because of various reasons, but that's the target. Once you hit the target, you break up the target nucleus, and you produce lots of particles. Ions are easiest to produce because they have very small mass, 1/10 the mass of the nucleus of proton. So lots of ions get produced. And then you can use magnets to take out ions of a certain charge or a certain momentum. Use magnet to choose your beam of ions. So that's the kind of beam of ions. Okay. And now what you do for these antineutrinos, that you make a beam of ions, let these ions decay. Okay. So you have ions going with very high speeds. So when they decay to muons and neutrinos. So because of relativistic boost, neutrons will also go in operating the same direction. So you get boosted ions and boosted neutrinos. And that's how you get it. That is still the way to create a muon. So here we have our second family. So after this, things were not so exciting in the sense, once people knew two families, people expected that even when we have a third family, we will see neutrinos both. So you will notice that the third neutrino, which is tau neutrino, was detected only in 2000, which is very, very recent. Okay. Even before it was discovered, it was sort of accepted that in the atmospheric neutrinos, news go to new towns. People didn't even they didn't even think before they didn't even have an idea before saying this. However, just for completeness, we had this experiment at Fermi-Lab called the donut, which did use very similar reaction, mu tau on nucleus meeting to tau and some other nucleus, and they will detect this tau. Detection of electron and muon is usually very simple. Okay. You can photo electron to some trap. Muon also can give you some trap. Muon also travels very, very fast, so you can get very large traps. Problem with tau is that tau decays. Okay. It doesn't decay to nice particles. It decays to pions. Okay. Many pions, 3 pions, 5 pions. Okay. It's very difficult to identify energies of pions, for example. So it's even though you see lots of pions in the detector, it's very difficult to distinguish them from background. Pions are always hard to. The only way you know pion is tau is you look at all the pions, you find out what the original invariant mass was. It was tau mass, then it's tau. But then it's very hard to do because firstly pions are hard to detect. Secondly, when the tau decays, it will decay also to a new tau, it will be new tau. So you won't be able to see the whole energy of tau that has decayed. So you can never reconstruct tau particle completely. So it decays before you can see the track, and once it decays, you can never see its complete energy. Okay, so therefore it's very, very difficult to identify tau particle energy. That was one reason that this experiment took so long to identify it. So it was as recent as 2000. New tau. Okay. But they won't even know it. It's not very exciting. Everyone knew that there would be new tau. And this was just taken as an experiment. Completed.
How do we produce new taus? How do we produce new taus?
Tau decays. Yeah, in fact, this is the way it was done. Produce tau, make a beam of tau, and the tau will be. So this is the way that we normally detect neutrinos. There are lots of different detectors, and we will come to that. But this is the standard. So this is super conductance detector, which is the largest one we have currently. The detector is 40 kilotons of water, which corresponds to 40 millimeters. So it's the size. If you look at the volume, I think it's similar to A block. Basically, AF was A block. fill it with water, it will be about 40 kilometers. So you fill that up with water. All these you see around are phototubes. And what's going on here is that is people are sitting in the boat, they're trying to polish the phototubes. The way to polish the phototubes is put in water, start increasing the water level, then you go around all these phototubes, polish them, increase water level by whatever, 2 more meters, go to next meter. So I want you to appreciate that the number is rather large, detector is very large, and it is covered in all phototubes. The phenomena used for detection of neutrinos is Cherenkov radiation. So what happens is, so you know Cherenkov radiation. Cherenkov radiation is familiar. So if a particle is traveling through water and its speed in water is more than speed of light in water, it will give you a Cherenkov. So what you do is, when an electron comes, when a neutrino comes, it hits an electron. Electron gets a large velocity, almost the speed of light. But of course, the speed of light is less. So electron gets a velocity equal to c, 3 times 10 power 8 meters per second. Speed of light in vacuum is about 2 times 10 power 8 meters per second because of the refractivity. Okay, so therefore, the electron will be traveling much faster. So therefore, we will get a Cherenkov. So this is a new coming, interacting with electron. Electron travel very fast, therefore it will give you cone of light waves. So finally, if you look at the surface of this superconductor, you will see a circle. So that's the way you normally detect it. The slight detail involved, which maybe I should mention here. See, electron will not only give you Cherenkov light, it will also lose energy by radiation. Okay? So therefore, the ring that you get for electron is not very sharp, it's diffuse. Okay? That's just on the other hand, if it's a muon, okay, muon doesn't lose energy that quickly. Therefore, from muon you get a very nice circular ring. Electron will get a diffuse ring. This will come in handy because it's very useful in distinguishing electron and muon. So detector like this, therefore, can distinguish between electron and muon. However, it won't be able to tell you whether we have electron or positive, or muon or mu plus or muon. But electron and muon separation is public. So that's the kind of thing that we can do at the moment. So this is the largest neutrino detector right now.
I mean, in that sense, it will not be able to detect when it has detected a neutrino and
You won't be able to see. So all the results that superconductor has right now is when you combine both. So you add neutrino and neutrino, that's the process. And to give you some number, neutrinos passing through superconductor is about 6 times 10 to the power, this should be 10, I guess. So that's the largest one. However, in spite of having this large detector, you only see about 10 interactions per day because everything else is persistent. Yeah, but that's much smaller than this. The flux is much smaller. You get more events. I'll come to that. Events you will get similar number because we will give you about not 10 events per day. However, the flux is much smaller. Okay, so this was discovery of neutrinos. Now I just want to tell you about the major advances in neutrino physics that happened over the last 40 years. And advances came because there were problems, and while we tried to resolve these problems, we found something new. So I tell you what the problems were, and I tell you what the solutions were. And we discuss the problems in detail in future classes. This is just a quick overview. So I told you that inside the atmosphere, you get protons. Protons produce ions, and ions will give you decay into muons. Muons can decay into electrons. In this process, you get lots of neutrinos. You get some muon neutrinos, some electron neutrinos, and some muon antineutrinos. So in general, if you see here, since you cannot distinguish between neutrino and antineutrino at this stage, it is added. So then you say that you usually get one electron neutrino for 2 muon neutrinos. Okay, so mu flux is 2 times mu flux. This is what you would expect. So the experiments were done for about 10-15 years. But it was found that this ratio of 2 didn't quite hold. It wasn't exactly.
But here we are not considering the solar neutrinos at all.
Only at present.
How do we distinguish between whether mu E that we have is something atmospheric?
Because energy. So we know that solar neutrinos have energy of the order of MeV, maximum 10 MeV, 15 MeV. Atmospheric neutrinos have energy of the order of G. Because cosmic rays have charge energy. Therefore, typically atmospheric neutrinos have energy of the order of G given. It is 100 MeV. Second interesting thing that we can figure out, even without having to talk about mu and mu, is that number of mu's coming from top should be the same as those coming from bottom. So that's because the universe is almost isotropic. Protons come from all over the universe, it's isotropic. So if you see factor of 2 difference between neutrons coming from top and from bottom, you know there is something missing. So exactly that's what happened when you observe this. So we'll go through this thing in details. I just mentioned you what happened. So what happened is when you look at electron neutrinos, they work very fine. Whatever you expect, you find them. When you look at muon neutrinos, you saw that when muon neutrinos come from top, they are perfectly fine. Observe what we expect, almost. When they come from bottom, we see that some of them are lost. So when they pass to the earth, we have some visibility. So that's a problem. Okay. Yeah. One would say that they got absorbed in the earth. That would be one option. But we already know that the cross section of the thing is very, very small, so we can't be absorbed. So definitely there was something missing. So we, as I told you, we spent almost 2 lectures working on exactly on this. So at the end of that, we will find that the solution was actually very simple. Although
These results is corresponding to scope identification. So for that you will have to track the trajectory of the neutrino. To distinguish it whether it is from top or bottom.
yes, not neutrino, but say one that comes from top, it's an electron. Electron will move in this direction, approximately. So that's the way to do it.
Because and we cannot track its trajectory.
You can't track neutrinos.
Yeah, sorry.
But electron you can. So you only look at the trajectory of the electron or muon that comes out of the emission. So it's always true. In any neutrino experiment, you will only be able to see where the electron or muon moves. You will never be able to see where the neutrino came from. So this is the hindrance that you have to live with. There is no way that you can do it. So the solution to this was essentially this, that neutrino flavors, which is basically they mix amongst each other, and they have different masses. These were 2 predictions. Okay. And once that was done, and then of course UV are not affected because they don't participate in loss. So this is going to be the bottom line, and we will see in detail how we arrived at it. I just want to put them in front. So the net conclusion was that UV, mu's oscillated into u taus and not mu. So that means what will be the bottom line of solution to atmospheric. Once you do this, we can find out what is the mixing angle and what is the difference in the masses. So essentially, you do the experiment, you will be able to make these 2. Now you have to confirm that this is not because we did not understand atmospheric neutrinos. So you do other experiments which have got a short baseline, which means that now you make neutrinos at some source, detect device and detector, and then we check that they actually behave the way we wanted. So then we did these experiments, and then we found that this actually was true. So this atmospheric neutrino problem lasted for about 20 years and told us that neutrinos mix. So this was a very simple thing. Another important thing was the solar neutrino puzzle, which actually lasted for about 40 years. And the puzzle also was very similar to atmospheric neutrino. So we knew that inside the sun, inside the core, we have neutrinos produced. Effectively, you get hydrogen going to helium, so you have to have muons. So this is a detailed reactions, and you see that every individual chain that you have to go through inside the sun involves muons, electron. So, in some sense, they are essential for the sun to shine. And Davis made an experiment in 1962 to detect these neutrinos, and he showed that neutrinos actually came from the sun. He got a Nobel Prize for that. Again, not late, but he did get it. However, the number of neutrinos that he actually saw were almost half of the number of neutrinos that he expected. This was the problem. This was the mistake. So again, you expect this is energy of neutrinos, and this shows you data divided by expectation. So ideally, it should be 1. Data should just all lie here if you understand the sun well. It was observed that all the data was here. So which means that half of the electron neutrinos were lost. Now if they are lost, it means that all our knowledge about the sun is in danger somewhere. Because if we are able to calculate exactly how many neutrinos come, then only we will know exactly how much light comes. So to match with the light output of the sun, we must observe the neutrino, which was not possible. So which was not observed. Okay. So again, this was also a super clubbing project. We did not know where the missing neutrinos went, and then people thought that there was a problem with our understanding of the sun. Lasted for almost 40 years. It is now that we figured out that the problem was not understanding of the sun. The problem was with understanding of neutrinos, that they actually mix. So give you the bottom line. So bottom line is exactly the same. Bottom line is that neutrinos levels mix. They have different masses. However, here we needed something more. We needed that the masses and mixing angles of neutrinos should depend on matter density. Because it was very important that neutrinos were not inside the sun, not outside. We are going to spend about 4 lectures on this. So we will go through these things again. So although the atmospheric and solar problems should be very similar, solutions are very different. Okay. So solar solution, for example, is not a solution which is not possible. So we will come to it when we actually do it. So if you look at atmospheric neutrinos, yeah, I'm finishing that. If you look at atmospheric neutrinos, you would have seen that there are oscillations like this. Perhaps not very visible. In solar case, there are no such oscillations. So that's a distinguishing feature, which again you come to some. However, again very similarly, this will give you delta m square, will be mixing angle, and you will do an experiment on one, producing the neutrinos somewhere and confirming that condition.
So you are using the delta m square. That's the mass difference between two neutrinos.
No, there is a difference in the mass squares of the two neutrinos. Okay, so it's this particular quantity that will actually come in. So I just showed you this thing in brief and then we will stop. So this is a summary of current knowledge. Solar neutrinos gives us some delta m square and angle, mixing angle. Atmospheric one gives you some delta m square mixing angle. and reactor neutrinos also we can find, but then in these experiments we don't see any neutrinos lost. We observe everything that comes. That's another puzzle. You know, if these two things get lost, why don't something from reactors get lost? The reason for that corresponds to some third angle theta naught scale that is very small, and that's where our 3 neutrino officer come into play. So when we come there, we will understand what this is. So this is the last slide that I will show you. So what do we know? So we know that we have electron neutrino, muon neutrino, tau neutrino. They mix to form mass eigenstate that we call as U1, U2, and U3. It turns out that what the data we have allows two patterns that look like this. This is for normal, this is for inverted. And we don't know whether the mass ordering is normal or inverted. So we don't know this. We don't know absolute neutrino masses. As I showed you, we only know what is delta n square. We don't know if there are more than 3 neutrinos. It's possible that there is something else.
So it's similar like asking whether there is some other family that
actually it's much more than that. Okay, there are neutrinos which are not a part of family but something more, first sterile neutrino. We don't know if there is CP violation. We just got 2008 gave the Nobel Prize for CP violation in quarks, but we don't know what happens in it. And we don't know if there is some new physics hidden in the data. So in the first half of the course, we actually try to find out answers to all these questions. As to why fusion of neutrino physics we'll talk about when we begin the next class. So we'll stop here. Have any questions? Good, we can ask.
But if you are mixing angle with the angle, what is visible angle? I mean the angle of neutrinos.
Yeah, so simply it's like this. So you have two neutrinos, electron neutron and muon neutron. However, they are not mass eigenstates, which means that if you want to look at neutrinos with mass m1, then this neutrino will consist of some fraction of mu e, some fraction of mu b. These fractions are called them as cos theta sin theta that mix. So the exact meaning we will look at it when we come to atmospheric neutrinos.
The fact that theta 1 is small, is that we know from atmospheric?
Yes, but indirectly. For that you have to do a detailed analysis of atmospheric neutrinos. It's very simple to understand atmospheric neutrinos only 2 neutrino framework also without worrying about theta 1.
Yeah, but if you take the neutrino, then you can't be know that.
You can, but you won't know that it's so small. You will be able to say that it's not 40 degrees.
Small compared to the
Yeah.
other. In that analysis, you can only say it is small compared to the other.
Right. That's true.
The case will be 45 degrees.
The actual atmospheric angle measured is almost 45 degrees. Again, we'll see exactly what 45 degrees is a mnemonic. Okay, it's anywhere between 36 degrees and 54 degrees. We'll learn exactly how to handle these things.
So the three values, they are not the answer is not a kind of puzzle that we were getting from Harriet. We were getting a full neutrino. In some sense, it's also a puzzle. Why are we getting Harriet?
True. Yeah.
So the question in every puzzle was same. I mean, whether I'm getting sort of neutrino fluxes, neutrinos, whether the other neutrinos are coming. But the answers are coming from other sources. I mean, in some cases it's oscillation, in some cases it's a matter density issue, in some cases it may be something.
But still, we will finally have one framework which answers all these questions.
That still we don't.
No, we have it. We'll come to the answer.
I mean,
We'll come to the answer. It will take us about half the course, but at the end of half the course, we will come to the answer. This I can guarantee.